When astronauts fly in space, they are dependent on familiar liquids and gases like oxygen to breathe, water to drink, and then they are limited by other gases like carbon dioxide. And so getting oxygen to the astronauts to breathe is very conducive for their long-term survival in space. And right now this is done with fairly large, complicated machinery that is prone to wear and tear and requires a lot of spare parts to be swapped out. My guest today is Alvaro Romero-Calvo. He is a professor of aerospace engineering at the Georgia Institute of Technology. He and his team have been awarded a NASA NIAC grant to develop a magnetohydrodynamic drive that actually is used to be able to separate hydrogen and oxygen out of water in a way that has no moving parts. And so it doesn't require that standard servicing from all the wear and tear. And so in theory, you'll be able to have a small amount of water, oxygen as part of a closed loop environment in your spacecraft for a long journey to Mars to be able to reuse it. Now, we talk about his NASA NIAC grant and what his plans are for that, but then we also talk about just like how fluid works in space in general. And that leads up to us talking about how refueling might work in space. And this is really important when you think about how Starship is going to be trying to refuel in space for sending humans to the moon. So it's a fascinating conversation about the specific technology, as well as just how fluid works differently in space in the ways that we're expecting. All right, enjoy this interview with Alvaro Romero-Calvo. Alvaro, how do fluids behave in space in a way that is sort of different or similar to the way they behave under the more familiar gravity of Earth?
Well, they behave in a very disordered and chaotic manner. It is always surprising and hard to predict. You have to realize that when we are in an orbit in a spacecraft, fluids are not subject to buoyancy, so you don't feel the effects of gravity. That doesn't mean that gravity doesn't exist in an orbiting spacecraft. It means that gravity is not effectively acting on your system. So, well, you know, if you are drinking a glass of water on Earth, water will always flow to the bottom of your glass, and that's the way we are used to see things happening, right? In a space, that is not the case. In a space, water tends to be dominated by a force that is the surface tension force, or capillary force. The same force that makes insects walk over water in a pond or in a lake, right? So it becomes really interesting really quickly and very unpredictable because it depends on factors that are hard to control and hard to measure.
I mean, I know that one of the questions, like before astronauts actually went to space, we didn't know if some of these very basic things were actually going to work. Could people drink in space? Could they swallow? Could they eat? Could they pee? Could they go to the bath? Like we didn't know all of this stuff, and it all did work, but there were some surprising differences.
Well, there is something interesting about this field, right? So we named this field low gravity fluid mechanics, but in the end, low gravity fluid mechanics is no more than capillary forces, right? It is the same physics that govern the behavior of liquids in microgravity are the ones that govern the behavior of liquids in microchannels in your capillaries, right, in your blood vessels. So essentially, we knew capillary forces before the space era. We have been studying capillary forces since the 19th century, right, the Laplace-Young equation and all that stuff. So it is not like we didn't know what was going to happen, but this is the beauty of this field. You don't really know what is going to happen until you are in space, because what we call the boundary conditions or the external factor influencing your problem are determining your solution up to a crazy degree of accuracy, right? So a tiny variation in the way your fluid is located or in the way your fluid is subject to external accelerations will radically change the behavior of your system.
So I want to sort of talk about that. Like we are familiar with these capillary forces. I did an experiment as a kid where you would like put pen ink on a piece of paper and then you would put it into water, and then the water would rise up in the paper and sort of separate the ink out into different colors of the rainbow. You know, there's lots of situations where you do these science experiments where surface tension is the dominant force as opposed to gravity. But in many cases, because gravity is so strong, we just aren't familiar with it. But when we go to space, like how do I'm trying to understand how things behave when surface tension and capillary forces are just the only way that fluid are going to move around. how does that change your thinking about a machine, about the way pipes work, about kind of everything related to fluid on like the space station?
This is the key of this, right? I mean, we lack, or at least until the beginning of the space era, we lack an intuition of how things behave. And even today, most space engineers lack that intuition. You really need a lot of experience and a lot of contact with the microgravity environment to start figuring out how things move in space, right? Essentially, when you create a soap bubble, right? The soap bubble adopts a spherical shape. And this spherical shape is dominated by the surface tension forces. The sphere that it creates is the minimum, what we call the minimum energy configuration. That means that the system likes to be there. In space, the same happens. Liquid interfaces in general like to become spheres, like to become bubbles and droplets and float around and so on, right? But that is not the only thing, because, okay, the liquid itself is trying to be together as much as it can. That is the cohesive force, right? But when the liquid touches a surface, like the walls of a propellant tank or like the electrolytic cells of the ISS, right? Interesting things start happening there. The liquid starts wetting the surface or being repelled from the surface, right? Depending on whether it is hydrophilic or hydrophobic. So there are many, many factors in here. And it is, in essence, from a fundamental science perspective, it is a very beautiful mathematical problem. In practice, it is a total nightmare, right? Because suddenly you don't have
right.
the force of gravity to help it, right? So it is always complicated to try to figure out a good way to make our systems work in space. Let me give you an example. So imagine you want to drink a cup of coffee in space, right? Easy. I don't know you know this, but the pleasure that we feel when we drink coffee, it does not come from the taste of coffee. Coffee has actually a pretty bad taste when you figure it, right? So actually, we enjoy drinking coffee because we smell coffee, and the smell of coffee is something wonderful, right? If you go to space, you cannot, in principle, drink coffee in a coffee mug because there is no buoyancy. So gravity is not pulling the liquid to the bottom of the cup. So if the astronauts try to put coffee in there and they try to drink it, there is no force that can bring the coffee to their lips, right? So the solution traditionally has been taking a plastic bag, putting the coffee in there, and then sucking the coffee from the plastic bag after warming it up in a coffee machine. There is a fun experiment with Samantha Cristoforetti, the European Space Agency astronaut, and Lavazza, where they prepare an espresso in space. And you can see the pictures, and they're actually holding the espresso in a plastic bag, like the ones you can find in a hospital, for instance. But yeah, the pleasure that you can get out of that is not, it is not your morning coffee, let's say it that way, right? So a friend of mine, Mark Wislogel, based on the experiments by a NASA astronaut, Don Petit, came up with this wonderful idea of creating a space coffee mug, right? This is what they essentially did was generating what we call a corner geometry or a wedge. The idea is that liquids tend to be attracted to those wedges, including coffee. So I encourage you and our listeners to go online, look for the coffee mug, a space coffee mug, and they will see a wedge geometry surrounded by a circle, right? So the idea is you put the coffee in there, the coffee tends to go to the corner, and as a consequence of that, you can drink it, right? And there is a beautiful picture out there of Samantha Cristoforetti drinking her Italian coffee in space with Mark Wislogel's coffee mug. So it is a beautiful application of capillary forces, right? But in order to get to that point, you really need to run a ton of simulation. You really need to understand how that system is behaving, and that is non-trivial. And I think that's the problem in the end, right? We could we can design as much as we want on the ground, but this requires an iterative approach because you never know very well the boundary conditions. So it is always very interesting to face these challenges, these problems, because there is never an obvious solution to them. That is the beauty of this field and the nightmare, as I was saying before.
Right. Yeah, of course. Now, so I'd like to shift gears then and actually talk about the NIAC grant that you were recently awarded. What are you attempting to study?
So our focus is oxygen production for astronauts. So imagine this. We right now have astronauts at the International Space Station who are breathing oxygen every day and producing carbon dioxide. And that is part of a closed loop life support system. right? In the Mercury era, we just took a sort of scuba tanks, right? Scuba diving tanks filled with air or oxygen. We put them in the cabin and we slowly released the oxygen so the astronauts could breathe. But that has a limited time span. I mean, after a certain amount of time, you need to bring so much oxygen that the up mass of your system becomes totally unfeasible, right? So it is not a feasible approach for long-term space travel. In particular, for the trip to Mars. So you are going to Mars, okay, you spend 6 months, give or take, going there, do whatever you have to do in there, and then come back. So we are talking about a year plus mission. During this time, our astronauts need to breathe. And that means most of the time that you will likely want to have a bioregenerative or a regenerative life support system. What that means is that you want to keep the cabin as close as possible. Think of it like a submarine, right? A nuclear submarine. You are crossing the ocean. You don't want to surface in months or maybe years. Well, I hope it's not years. But you don't want to surface for a long time, right? So you need to reuse everything that you have within the submarine, or in this case, within the spacecraft. The astronauts like to say that today's coffee is tomorrow's coffee, right? So this is the same. This is the same idea. You want to recirculate all that. So you need to recycle all that carbon dioxide and that water, and you need to reuse it to produce oxygen. Now, the problem that we face nowadays is that the architecture, the systems we use to produce oxygen at ISS, at the International Space Station, are not as reliable or as efficient as they should be for a trip to Mars. There is a wonderful article by Jones at the International Conference on Environmental Systems where he analyzes how the current oxygen generation assembly at the ISS compares with just storing oxygen in tanks, basically in scuba diving tanks, for making it simpler. Okay? So it is very interesting because his conclusion is the current oxygen generation assembly weighs more than just storing all the oxygen for a crew of 4 in a trip to Mars. After you consider spares, right? After you consider all the spares that this system will need. So it is a very unreliable system, and it is not ready for a trip to Mars. So what we're trying to do in this grant at the end is, let's come up with a radically different architecture, a radically different idea to produce oxygen in long-term space travel. And that is our target.
So that's mind-blowing. That if you look at if you've read Scott Kelly's memoir of being on the International Space Station for a year, his greatest complaint is the levels of carbon dioxide, that they could just never get the carbon dioxide down low enough that he felt like he could think straight. There were bad days and then there were worse days. And there was never good days when it came to levels of carbon dioxide. And that was something they just had to fight through. And that is, you've got this system that is producing oxygen, that is recirculating the air, that is trying to absorb the carbon dioxide, trying to remove it from the system, then trying to use other chemistry to try and bring it back so that more fresh oxygen was being supplied to them. And so you're saying that if you want to do a trip to Mars, say a 9-month trip to Mars, 9-month trip back, from a weight standpoint, mass standpoint, it's actually simpler, cheaper, lower mass to just provide tanks of oxygen, pressurized tanks of oxygen, than to go through this whole rigmarole of machinery designed to try and recirculate the oxygen, break it up, break up the carbon dioxide, and absorb all of that. That's madness. That's crazy.
As of today, that's the case. So when you think, for instance, of a commercial airplane, the probability of a catastrophic failure by design is 10 to the minus 7, right? So 1 over 10 million. When you think of the probability of failure of a human-rated spacecraft, you're thinking more of the order of about a 1%, give or take. Which means that every system on board has to be reliable up to far more than 99%, right? So 99.9%, say. Which means that if you have a component that is prone to failure, that means that you will need to bring many spare parts to reach that reliability level. That is what drives the mass up in your system. That is why we can't. It doesn't mean that storing oxygen is efficient, because it is not. I mean, we're still talking about tons of mass. This is the main thing, right? We need a better system. That is why we propose this concept to NASA.
So how is the system that you're planning different from the kind of system that's on the International Space Station?
So, have you watched this movie named The Hunt for Red October?
Yes. Long
With
time ago.
With Sean Connery. I was watching a clip in YouTube about it, and there was this YouTuber who said, "Oh, this is the first Soviet submarine commander with a Scottish accent." Right? I thought that was very funny. But yeah, it is a beautiful movie, and the whole premise of the movie is let's build a magnetohydrodynamic drive to propel submarines. So what is that thing of a magnetohydrodynamic drive? Well, it turns out that if you take an electric current, right, you take two electrodes, immerse them in an electrolyte, like a salt water electrolyte, and then you put a magnet below that, you will start seeing that the bubbles move in a very weird way, right? The bubbles that are produced in this sort of electrochemical setup start spinning around. That force that makes the bubbles spin around is the Lorentz force or the magnetohydrodynamic force. And on Earth, you could engineer a way to produce or build a submarine that is propelled by that, right? So it has no moving parts, it's totally silent, and that makes it basically undetectable. That is the premise of the Hunt for Red October. Luckily, the concept on Earth is not feasible because seawater is not sufficiently conductive and because our current magnet technologies don't produce a sufficiently strong magnetic field. So it is a very, very poor concept in terms of engineering efficiency. On the contrary, in space, remember, we don't have buoyancy, so we don't feel the effects of gravity. What that means is that any force, no matter how weak or how small it may seem on Earth, becomes dominant in space. So you can start moving liquids around with all sorts of crazy physical interactions that we are not even aware of in the at the surface of the Earth, right? One of those interactions, the interaction we're exploiting in this program, is the magnetohydrodynamic force. So this is the idea. We have a liquid electrolyte, KOH. It is a conductive electrolyte. It is the same sort of experiment that when you are in high school, you pour salt into water, take two iron nails, put them in the water, and apply a current and see bubbles going up, right? So this is the same, but a bit more sophisticated because instead of that experiment, we're actually producing hydrogen and oxygen from water. We are splitting the water molecule. So we do that, but we apply this magnetic field in between so that we can start propelling the liquid. And we do it in such a way that bubbles generated at the surface of our iron nails, our electrodes, get separated automatically. And you may wonder, okay, why is this crazy guy telling me all this about bubbles and magnets and so on? Well, the key of this is that you can effectively separate bubbles without moving parts, without pumps, without centrifuges. And that is in sharp contrast with everything that has been done to date at the oxygen generation assembly at the ISS, for instance, right? In that particular system that is currently on orbit, you circulate the electrolyte, the water with the salt, sort of speaking, so that you can eventually separate the gas from the liquid. Now, that circulation loop consumes a lot of power because you need pumps. It's prone to failure. And in fact, every time you replace a pump, after 6-7 months, you need to be thinking about a new one because the performance degrades in microgravity. So it is a bit of a nightmare. So this is the bottom line of what we are doing in here. We are trying to increase the reliability of our system by replacing that complex loop with something that is touchless, that is completely reliable and doesn't require any moving parts. That something is the magnetohydrodynamic force. That is the main thing we are proposing to NASA.
And I mean, I think about on Earth when we used to do, like, again, science experiments where you would produce carbon dioxide, and you could see that the carbon dioxide was heavier than air and would sink to the bottom of your aquarium tank when you're doing the experiment. But again, all of that goes out the window because we're back in space and there's no gravity, and so we're not going to get any buoyancy of different gases compared to each other. But you can separate the oxygen and the hydrogen from this electrolyte purely through the magnetohydrodynamic force acting upon the individual ions as they're coming off.
Yep. Yeah. So the idea is it is like a washing machine, okay? The only thing is that we are not spinning anything mechanically. We have a magnetohydrodynamic force acting on a disk. It is actually, our electrode is very weird because it is not a flat electrode as you can see on Earth. It is a ring, okay? And this ring has magnets on the side. And the idea is that the magnetohydrodynamic force spins the liquid right, in microgravity. Now, when you spin something, there is one thing that happens immediately afterwards, which is the centripetal force, or depending on the reference system, the centrifugal force, right? And what is happening here is that we are producing bubbles of hydrogen and oxygen at the same time as we are spinning the liquid. And when we spin the liquid, those bubbles flow towards the center of our ring, where we extract it. So that is the idea. There is nothing moving in there besides the liquid, but we can separate them very efficiently.
But I mean, don't they want to recombine? I mean, oxygen and hydrogen are, if they get close, I mean, that's rocket fuel, right?
Yeah, no, and that is a great question. That is the main concern that we have with these technologies when we send them to space. That is another reason why progress in this field is so complicated, right? Safety. So the way we prevent that is using a styrofoam membrane. So a membrane that separates the hydrogen and oxygen so that they cannot merge together, right? And that is done in different technologies. It is done in a different way. For instance, there is the competing alternative is a proton exchange membrane. Proton exchange membranes have a natural barrier between hydrogen and oxygen. In our case, we need to produce that barrier, right, by imposing a membrane between the electrodes. But that's a problem that has been that has been solved, right? The Russians have a hydrogen and oxygen production module called the electron module, right? And it uses a very similar technology to ours without the magnetohydrodynamic component. So they just have an alkaline electrolyzer, and they solved this problem many, many years ago, right? Probably not as efficiently as to make it feasible for a Mars transit, right? But certainly up to the point of being able to operate that safely at the International Space Station.
I mean, it's interesting. Hydrogen is a famously tricky gas for rocketry, and especially going into space. It tries to get out of everything. Yep. And so you can sort of take advantage of its ability to escape better than oxygen as a way to separate the two atoms from each other.
Yep. Hydrogen is a total nightmare of a gas. It takes the valves that we use to control hydrogen are very heavy and bulky, because even the tiniest gap in any fitting will leak hydrogen, right? So it is very, very complicated to work with it. Sometimes it can be dangerous. At the International Space Station, nowadays, we vent most, if not all, of the hydrogen to space, right? In the future, there are plans to reuse that hydrogen, right? to recombine it in a further process, like the Sabatier reaction and so on. So that is... that's definitely planned. But yeah, I fully agree with you. I mean, you need to be careful with hydrogen. It's a very small molecule. It likes to get everywhere.
Well, and I guess that was my next question, though, was that if you're going to try to create a truly closed loop environment on this mission, I mean, you don't want to lose that hydrogen. You can recombine the hydrogen with the carbon dioxide once you've split up the oxygen from the carbon dioxide back into water, and then the astronauts can drink it, and then they're going to pee it, and then you're going to break it up and you turn it into oxygen. So, I mean, have you thought about what the larger chemistry of a full closed loop environment might look like with this component as part of the system?
Yes, and in fact, that is part of our work in this NASA NIAC grant, right? And this is something that our colleagues at Giner Labs are helping us with. These guys are based in Boston, and they are experts in electrochemical devices for space applications. So we involved them into this program because they are the best in the field, right? And they bring a ton of expertise into not just building our little device, right, in a sort of academic fashion of analyzing how this works, but also interfacing it with other systems on board, like the Sabatier reactor, like the water supply system, like all that stuff, right? So that is part of our NIAC grant right now. We are studying. Okay, we have this concept that is very promising, right? Using magnetohydrodynamic forces to move liquid around and separate gases. Okay, that is fine. But many concepts like this remain in the drawing desk for long because it is not possible to scale them up or integrate them into existing architectures. So that is what we are doing in here is, okay, we have this, it is a beautiful idea, but can it work or not? And a big part of that question is, can we integrate this into the International Space Station or an equivalent future system on a trip to Mars, right? To make it work with the other systems. And so far, it looks like we can. We are, there are many constraints imposed by that system. Usually, you want to design everything together. In our case, we are focusing only into the oxygen generation assembly. So it is an interesting challenge to design this with all those boundary conditions, right? And it is very fun.
Mm-hmm, mm-hmm. Yeah. I mean, it feels like that's where we have to get to if we want to truly live in space for long periods of time, where getting our hands on additional water, oxygen, and so on is a big problem. We have to learn to live in some sort of balance. And then, of course, these kinds of lessons will help us live more in balance here on the planet that we're on. So let's sort of take this into the future. So the astronauts complete their 9-month journey to get to Mars. They land on the surface of Mars. Will the system give them any benefit once they're in the 1/3 gravity on Mars?
That is a beautiful question. So, okay, in an electrolytic cell, in a water splitting cell, you have electrodes, right? And these electrodes are producing bubbles that, due to the force of gravity, get detached and go to the surface of the cell, right? And that is how we separate them there and on Earth and in many, many other applications, right? We just let buoyancy do the job, and that is fine. Now, the thing is, as you mentioned, the Mars gravity is much reduced. So let's say that the driving force for the detachment of those bubbles is much weaker. So that has two basic consequences. The first one is that when the bubbles get detached from the electrodes, they are larger, significantly larger, which means that they cover the surface of the electrode. They generate a sort of froth layer in front, right? And they take longer to go up, driven by buoyancy. And the main consequence of that is that you have now two electrodes, and they are trying to transfer current between them, or they are trying to get liquid into the electrodes, and they can't because there is a ton of gas in between. So the magnetohydrodynamic force, not in this particular application we're working on right now, is for microgravity. We have other projects aimed at high gravity conditions like Moon, Mars, or even the Earth, right? The thing that we're trying to do is, okay, let's try to remove these bubbles much faster, right? So that we can liberate this space and feed our electrodes with a very much needed water or electrolyte, right? So this particular architecture cannot be applied to a Mars surface because it is not designed for that. In a Mars surface, however, you will find a ton of problems with the reduced gravity environment. And by the way, it is not something we have been able to study very well, because there are not many many partial gravity facilities on Earth we can use to study how this reduced gravity environment affects different organisms, right? Or different technologies or different fundamental physics problems. And that's, by the way, one big problem, because right now, the Europeans have the drop tower of Bremen that provides partial gravity. The Chinese have just built a drop tower that provides partial gravity. In the US, we have parabolic planes that provide low quality gravity, like we are flying one this fall. But it is complicated to get to that point where you actually get, hey, this is the low gravity condition, this is my test, and this is what we got, right? We don't have good testing facilities for that.
It is amazing that there isn't some experiment, some centrifuge in space where you can perform these kinds of low gravity experiments. Like, if we really are going back to the moon and eventually going to build a research station, and if SpaceX is truly going to be sending humans to Mars to build a giant city, there's so many unknowns that we have no idea how things are gonna play out. From a broader perspective, when you think about humanity living on other worlds, what is something that sort of feels to you like is a nightmare that maybe people haven't even thought of yet? I sort of think about from a, like when people always ask, oh, I can't wait to see humans living on Mars. I'm like, well, but there's so many things left to do. Like, how are we going to get them power? How are we going to be able to dispose of waste? How are we going to be able to grow food? How are we going to be able to go to the bathroom? What are the effects on biology of humans gestating in lower gravity? Like, we just, increase amounts of radiation, in situ resources. Like, it goes on. I could write a list of 1,000 things, I think, of problems that need to be solved. What are some problems when you think about sort of humanity's long-term existence in space, where you just go, oh, we don't even know where to get started on this problem?
Wow, where do I start? Okay, you have made a very comprehensive list in there, so I'm pretty sure you're aware. Okay, so number one probably is radiation, right? So radiation, in particular, in the trip to Mars, because once you are at the surface of the moon or Mars, you can always hide under a lava tube, or you can build a shield. There are many things you can play with in there, right? Or you can even build a sort of bunker for events of high solar activity, so that you can avoid the flux, right? But it is really, really complicated. You know, I teach space systems design here at Georgia Tech every year, and it is one of the things that the students suddenly find out is like, oh wow, actually radiation is something that is very nasty to deal with, right? It's like, how do we deal with this? So there is no technology, surprisingly, nowadays that can deal with that in a long-term space travel. We can try to mitigate it, particularly the low-energy particles, right? But gamma rays, it is impossible to shield those. And high-energy particles, like galactic cosmic rays, cannot be easily shielded either, because what you can add, 3 meters of lead between you and the space environment. But even when you do that, there is going to be a sufficiently energetic particle that gets in there and generates a cascade effect that in the end becomes worse, right? Your dose is going to be even higher. So this is not like, okay, let's add more mass, and in that way we bring down the curve of dose over time, right? No, at some point it kicks back up, right? Because there are other secondary effects happening in there. So really, radiation, at least passive mitigation strategies, are not the solution, say, 1,000 years from now, when we are effectively an interplanetary species, right? We will probably need something active, but as of today, the technologies we have for that active spacecraft control of radiation are not ready for that sort of mission. So that is number one. Radiation is number one, right? Number two, probably, and this is something that people don't think about, and part of the reason is, okay, I'm an engineer. As you know, engineers are not very famous for being great humanists, right? So we don't design usually with psychology in mind, and that is a mistake. It has been sort of a trend in the space era, but psychology in space is very important. Think about this. You are going to Mars. You are spending there, I don't know, 4 months and then returning. So total of 1 year and a half trip, give or take, right? The psychological aspects that go into that are very, very interesting. The isolation, the lack of a window, the lack of a tree, of a mountain, right, of a lake, the things that make us happy. Those aspects are extremely important, and studying them is critical. And in fact, that is one of the reasons why we run analog studies, right? Where we take a bunch of astronauts, we put them in a bunker for 6 months, 1 year, 2 years, and then we let them out and say, hey, how did it go, right? So it is the psychology of this is very important. I remember this NASA technical report where they study, okay, what are the things that we need to put into a future Mars colony, right? Based on one of these ground analogs. And they were listing them, and they said, okay, actually, we don't need so much space, but we do need a window to see the outside, because otherwise this becomes extremely claustrophobic, right? So there are all these sort of design variables that we are never really accounting for very well. And we're gonna really find them when we send astronauts to Mars the first time. We figure out, okay, how did it go, right? How did everything go?
Yeah, it's funny. There's like a series of experiments in isolation tests and things like that, and the result is always depression, anxiety, anger, breakdown in teamwork, and so on. And like those experiments, it's almost like they don't even need to be run anymore. Like we know what happens to human beings in isolation, in small groups. They get very stressed out, and they get they have a really hard time working as a cohesive team, and that you really don't solve those problems until you have a lot of people, and ways to get away from a lot of people, and yet ways to also be around other people. And there's this show they film on my island, on Vancouver Island, called Alone. I don't know if you've ever seen this show, but they have some like survivalist wannabe go and spend time on Vancouver Island in November, and it's really hard to be out in the forest that time of year. It's very wet and cold, and there's not a lot of food, and they're all so gung-ho going into it, and then a month into this, they all just want to go home. They just want to go home. They just want to see their family. They're sick and tired of this. And it doesn't matter how much money they're going to win. If they can just stick it out and beat all the other people, they can't take it anymore. And it's interesting to sort of think about that. I mean, I think that for a lot of us, as we sort of imagine our future out on Mars, it could be like it's going to be just like Earth, except I'm on Mars. And how cool would that be? And I'm living the sci-fi dream. But it is just, it's so extreme and so difficult and challenging. And we have such a gigantic to-do list. So
yeah, anyway, that's... have you watched Lost?
Yeah.
Do you remember Desmond? All the life pressing a button, right, in the bunker. So
yeah.
It is the same, right? And that is, in fact, one of the reasons why selecting astronauts is so complicated, right? You really need to hit the jackpot of psychological abilities to find the right person, right? Someone who is prone to collaboration, someone who doesn't get offended or pissed off very, very often, right? Someone who can handle that pressure, that isolation, that carbon dioxide level, and also someone who knows what they're doing technically and who are very proficient, sportive, and so on, right? So it is certainly one of the most commonly ignored aspects of space exploration, right? So the psychological aspect is very, very important.
Yeah, totally. So I want to shift gears and talk a bit just about propulsion, because you started off talking about how this is the Hunt for Red October. This is a Magnetohydropropulsion drive. And yet you're not proposing to use it as a drive. You're proposing to use this technology as a way to separate hydrogen and oxygen on a long trip as part of a closed loop system. So how does this kind of technology have an application for propulsion systems in space?
That is great. So our laboratory here at Georgia Tech works with CubeSat propulsion, right? With cold gas propulsion in particular. So cold gas propulsion is, in our case at least, we take a saturated liquid, like a refrigerant, right? Like the one you find in your fridge in a closed loop thermodynamic system that is cooling your fridge, right? So we use the same to propel a spacecraft. We just store that in liquid form, and that reaches a pressure, a storage pressure that is pretty high. And we use that pressure to get the gas out and propel the spacecraft. We provide little bursts of gas, right? But there is a real challenge with this, with CubeSats. So, okay, when you have a normal spacecraft, normal meaning a large spacecraft, a GEO satellite, COM satellite, or a LEO Earth observation satellite, or something like that, right? Your propellant tanks are going to be most likely spherical or close to spherical, for instance, ellipsoidal, right? And those are tanks that we have studied for over 60 years. So we know how those tanks behave with storable propellants like hydrazine, which is very nasty, by the way. Never get close to hydrazine if you can. So you can store that there, and it is going to be fine. Now, a CubeSat is a shoebox, right? It's a satellite that is very big, say a 6-unit satellite can be 10 by 20 by 30 centimeters. Pardon the metric system, but it's...
No, I'm Canadian. I don't know how anything else works. So,
well, so it is. So the CubeSat is very small, and when you want to put a propellant tank in there, you don't really have a space for a spherical tank. What you have is a space for what we call a conformal tank, right? So a tank that conforms to the shape of the CubeSat, that is a cube, a square, it elongates, and so on. So now, the problem with that tank is that because of the absence of buoyancy, it is extremely hard to separate the gas from the liquid, right? Again, it is the recurring problem in low-gravity fluid physics. How do you get only the gas out? Because remember, the gas is what is propelling your spacecraft. You can get the liquid out, but you're going to be losing a lot of propellant in that way because the liquid is not going to propel you. It is the gas what does. So there are many ways to solve that problem. None of them are really efficient, right? You can try to spin the spacecraft. You can try to take a heating loop, right, and vaporize the propellant as it is flowing through the lines, but it consumes a lot of power. So one thing we're doing, and this is another NASA grant, this is a tech flights. What we're trying to do in here is, okay, what if we apply heat to this saturated propellant at a specific location? Remember, it is saturated, so it means that it is in equilibrium with its gas, right? It's like if you have a vacuum, you put water in there, and you would suddenly have liquid water and gas water. So we're doing the same, but with a refrigerant. We apply heat, and we vaporize our refrigerant close to the heater. And now we put an outlet near the heater so that we get only gas out of there. And that is one thing we're exploring for CubeSats. It is important because we can increase the delta V, which is let's say the total velocity we can impart to our spacecraft, or the total it is correlated with the total thrust that we can apply to our spacecraft by up to 30%, right? Because we're making the system much more compact. So we apply this heat and the liquid is vaporized, and that is fine. We get the gas bubble in there and we get it out. Now the big challenge in here is that gas bubble will most likely, and I say most likely because we don't really know, will most likely be multiple tiny bubbles together. So now the question is, how do you merge them together into one, and how do you keep them close to the outlet of your tank? The way we're doing this, or one of the ways we're exploring in a series of upcoming parabolic flights, is let's use tiny magnets. Magnets have an interesting property. They repel most liquids because liquids are diamagnetic. So let's use these tiny magnets located near the outlet so that we push the liquid away and we get the gas into the outlet. So it is a complex architecture. Again, this is the thing with our field, right? You can try to simulate the hell out of it. You can try to add, you can have a supercomputer, start throwing stuff on it and get wonderful results, what we call colorful fluid dynamics, right? Instead of computational fluid dynamics. So you can do that. But the problem is, how do you validate your system? And the answer is you need to go to microgravity to validate your system. You need to test it in space. And that is what we're doing right now. We have all the computational stuff, and now we are actually flying test units to see how this behaves in actual microgravity conditions.
And the hope is that this will sort of fit within the CubeSat structure, but provide a 30% increase in like specific impulse. Like, is that what you're getting? Is a higher escape velocity of your propellant, or just a more efficient use of it?
No, not directly. The specific impulse depends on the propellant you use, on the geometry of your nozzles, on a variety of technical factors. But in this case, we are trying to increase the amount, the effective amount of propellant that we can have on board. That is another way to put it, right? As a consequence of us heating up the propellant, we also increase the pressure, which increases the effectiveness of our propulsion system, right? But the primary goal is not the specific impulse in this case.
How would this compare to, say, an ion engine?
Well, that's very interesting. So ion engines or any other electric propulsion technology will always be limited in CubeSats because electric propulsion is limited by power. So what limits a chemical propulsion system is the mass, right? The more mass of propellant you put in there, the more delta V, the more thrust you can produce out of a given spacecraft size, right? In the case of electric propulsion, it is not really mass, at least not directly, right? You have a storable gas that you use to propel the system, usually a noble gas. And then you use tiny amounts of it, but accelerate those tiny molecules at to crazier speeds. As a consequence of that, the specific impulse that you were mentioning before goes much higher, orders of magnitude higher than chemical propulsion. So in other words, for less mass, you can get more impulse to your system, right? But the problem, as I was saying, of electric propulsion is power. In order to do that, you need a ton of power. And specifically, CubeSats are limited in power because they're tiny. The spacecraft solar panels are very, very small. So there is not a lot of power you can gather from the sun to make this work. So yeah, it is a beautiful idea, but it is limited by that. And that is why, by the way, we are moving, or some people are considering moving to high-power CubeSats right now, right? So let's try to make these solar panels bigger, to make our CubeSat bigger, so that we can start using these fancy propulsion methods that make our system much more reliable, ultimately doing much more with a much smaller form factor, the CubeSat form factor, and distributed architectures and so on. By the way, there are many problems in there associated with increased power, for instance, heat rejection, right? Which is something we are working on as well.
Yeah, it's interesting. Most people don't realize, but radiating the heat is in some cases harder than generating the electricity, and both require sort of fairly large structures to be able to do this. But yeah, I can imagine CubeSats deploying wings in a way that we see spacecraft deploying wings as they're out in space. Alvaro, what are you obsessed with right now?
I'm obsessed with the beginning of the semester and having to come back to to teaching because I'm a bit late with my lectures. But no, apart from jokes, so okay, our laboratory works with fluids. So professionally speaking, at least, we are always looking for ideas. We're always thinking about the next fluid management challenge in space, right? And there are so many of them, right? It's hard to spot a single one. For instance, if you want to use a Starship to go to Mars or to the Moon, right? Part of the Starship architecture is just refueling in orbit, right? So you take two of them, you transfer the propellant from one to the other, and that is how you refuel the second spacecraft. Here you go, it can go to Mars, right? It is an idea that works on paper, but it is not a great idea in terms of the technical maturity of the technologies needed to make it work, right? So it seems very stupid, but we are transferring liquid oxygen and liquid hydrogen in there. So we are transferring through the pipes, right? And it has to go from one tank to the other. You cannot imagine how many challenges are there that we haven't been able to solve at this point. For instance, let me give you a couple of them. One of them, the liquid is cryogenic. It's very cold. It's getting through the pipe. The pipe is normally warm, right? So suddenly you have a shock, right? You have an extremely cold liquid flowing through a relatively warm pipe. The pipe structure will suffer, and the liquid itself will get vaporized. So suddenly you have all this mixed flow of gas and liquid flowing from one to the other, right? And believe me, that is not something you want to see in space. That is a source of many, many problems, right? But beyond that, okay, imagine that you can pass that, you find the materials, which is an art, to find the materials that work in that configuration, right? You find the materials, you push the liquid through, and it's fine. There is a second question then, okay? Cryogenic liquids have very low surface tension. The liquid oxygen, liquid hydrogen, they don't get attached to many things, right? So capillary devices don't really work very well with them in the same way that in storable propellants, capillary devices work very, very well. So you are getting the liquid or the propellant into a client tank, right? And this liquid is raising the level of the tank. At some point, you need to start getting gas out of there to leave place for the liquid that is coming from the servicer, right? Well, the challenge in here, and this is a very long challenge in space exploration, is how do you make sure that you only get gas out of that tank? Or in other words, how do you make sure you are not wasting your propellant? So there are many people working on this. My dear friend, Professor Kevin Crosby from Carthage College, and I won recently a NASA challenge to come up with an alternative with a technology to solve this problem, right? We propose a thermodynamic approach using acoustic waves. Very, very fun, very complicated. We hope to fly it one day, right? So we won this challenge a few months ago. I know there is another important professor in fluid mechanics, Professor Michael Dreyer, who retired this July. He is working on capillary meshes, right, to try to separate liquids and gases in this configuration. But again, it is a hell of a problem because it is super difficult to do this, particularly considering the fact that you cannot just send, I don't even remember how many tons of cryogenic liquids to space to test this, right? So this is what we are facing, right? If you, I, and the whole space community, if we are serious about sending humans to the moon, if we are serious about becoming a multiplanetary species, we need to deal with these problems, and we need to work on these problems very, very hard. And there is so much to do in there. It is so exciting, right? There are so many problems that we need to face that it's a very good time to do this and to work on fluid mechanics in microgravity, right? And very exciting from an academic perspective in my case, right? But of course, from a whole industrial perspective, how do we get the liquids where we want to get them in microgravity? And how do we make sure it is done efficiently and in a way we can rely on them? That is a question we have been trying to answer for 60 years, and we haven't been able to answer it yet. So yeah.
Are you suggesting that, the Artemis missions, the plan is to bring humans to the moon by 2026, and the landing system for that is going to be Starship, and the plan for Starship is that it's going to fly to space, go into orbit around the Earth, and then somewhere between 10 and 20 flights of other starships are going to refuel the human landing system so that it can then fly to the moon to be able to provide this landing service to the moon. Are you saying that this refueling process is perhaps going to be more complicated than people are anticipating?
Well, Starship and well, in general, SpaceX has accustomed us to wonders, right? I mean, nobody gave a cent about reusable launchers back in the day, and they are dominating the market right now, rightfully so, right? So it is. I won't say they are not going to do it. I know many SpaceX engineers. One of my students is going to SpaceX in December, is starting to work there on fluid management as well. I know they have great engineers and good people. But effectively, I think this is a much more complicated problem than just taking a hose and connecting two propellant tanks in microgravity, as we have done in the past, for instance, in ISS or shuttle experiments before, right? This is much more complicated. This is much trickier. And so far, and maybe someone can correct me if I'm wrong, this hasn't been yet demonstrated in microgravity. And we need to see two Starship flying to space, connecting with each other, and transferring this vast amount of cryogenics without losing liquid, without producing any sort of explosive vaporization in the tanks or anything that can damage the mission or undermine the goals of the mission. So yeah, effectively, it is not easy. It is not easy, and we had given the example of a Starship, but we could give many other examples in many other fields of space engineering. These problems are way more complicated than we think. And when, I want to see it flying, I'm looking forward to it, but I know, for instance, Professor Mo Kasemi at Case Western University, he works on the thermodynamics aspects of the propellant transfer, right? Wonderful work, beautiful thermodynamic, classical mechanical engineering work. Believe me, it is not easy to handle these concepts. So I wish them tons of luck, but it is not going to be a simple operation.
Yeah, but we'll know it's working when we see a flight successfully tank up Starship and return, and then another one goes out. Like, we'll know we're on the right track if this doesn't tear apart Starship as the propellant is being transferred.
Yeah, I think so. Yeah.
Yeah. We'll see how that all plays out. Well, Alvaro, it was an absolute pleasure to talk to you. Good luck with your NIAC grant and all of the other projects that you're working on. Enjoy the rest of this summer, and hopefully you'll solve these problems and then move on to phase 2.
Fraser, my pleasure. Thank you so much for inviting me to your podcast, right? And thank you so much for everyone who listened to this interview. I hope to see you soon.
I hope you enjoyed this interview with Alvaro Romero-Calvo, and we're going to put a bunch of links so you can go and check out more of his work. I'm going to give you some thoughts and reflections, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bill, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I'm really glad I got a chance to talk to Alvaro about this, because this whole idea of propellant and closed-loop environments, these haunt me. I think about just how complicated this stuff is. And, he mentioned that people have been struggling with the idea of transferring propellant in space for 60 years. Really, for the entire age of spaceflight, people have known that transferring propellant is a top priority, and we need to figure out how to be able to do this. And there was this work done by United Launch Alliance like a decade ago where they were proposing building propellant depots in space, and it kind of never went anywhere, which is too bad, because a lot of that knowledge and learning really should have been gathered by now, when we're in this moment where we have to transfer mountains of propellant to be able to send humans to the moon. And there's just all of this underlying knowledge that we just don't have. And so much of it would be made better by having some kind of rotating science experiment that we could perform various levels of gravity in space. There's just so much to learn. And I think that on the one hand, we're really enthusiastic and excited about being able to go and fly to other worlds and send humans to Mars and so on. And yet the list of things to solve just keeps increasing. And really, we need to make practical progress on so many fronts at the same time. And so I'm excited when people come up with really clever ideas to solve some of these problems. And it just reminds me of how much work is yet to be done. All right. I hope you enjoyed the interview. We'll see you next time.